Hello and welcome to another Sonic session. I have this piece of code in Rust that generates a circle. Actually, it's a very simple piece of code, and what it does, it simply generates a circle pixel by pixel, and we can try to run this piece of code. First of all, you need to compile it, of course, and as you know, if it compiles, it works. Everybody knows that. So yeah, we need to wait a little bit because I need to warm up some caches and stuff like that. Okay, so let's actually run the entire thing. And as you can see, it generated a bunch of images for different patterns and stuff like that. But I'm interested in one specific thing that it generates. It's a solid circle. So it's a solid PPM. So let's take a look at it. So I'm going to run feh. I'm going to set the background to black so it doesn't fuck up the encoding. And we're also going to force aliasing so we can see all of those individual pixels, juicy pixels. So this is how it looks like. Pretty straightforward, pretty simple. But again, speaking of juicy pixels, this entire thing is very, I don't know, pixelish, pixelated. So it is not anti-aliased at all. Right. And recently I was just looking on the internet. How do you do anti-aliasing? Anti-aliasing. So I think specifically I was looking for spatial anti-aliasing, right? And I clicked on that link and I read the first paragraph of this sort of like section, right? The most basic approach to anti-aliasing in pixel is determining what percentage of the pixel is occupied by a given region in the vector graphics and so on and so forth. And this is actually you know, struck me. I don't know how to say that, but it gave me an idea that it's not that difficult to implement in that specific piece of code. Where is the piece of code? I think I lost the piece of code. And speaking of, this piece of code was written on the stream. If you're interested in how we develop this simple piece of code, you may probably want to go and watch the previous stream. So it's available on Sodium Daily, and the episode is called Programming in Rust, right? So this is what it's called, Programming in Rust. So, and I'm going to put the link to that episode in the description, right? So previous episode where we implemented the circle renderer, right? So you can watch it in here, and the source code is available on the GitHub, so you can grab the source code in here, right? There we go. So, and the topic of today's session is going to be just trying to implement anti-aliasing for that specific piece of code using this idea where we just try to approximate, like, or determine what's the percentage of the pixel is occupied by a circle, right? And based on that, we can, for instance, dim the color of the pixel, right? Or maybe it's put some sort of alpha in there, and then maybe achieve some sort of anti-aliased effect. So that's basically the goal of today's session, right? Because it sounds relatively simple, and I wonder if it's going to be also effective. So yeah. That's pretty much it. So let's go ahead and start working on that. So in this specific piece of code, we already do a little bit of a subpixel math, right? So specifically we're determining the distance from the center of the circle to the center of the pixel to see if that pixel needs to be included in the picture or not, right? So let me actually show you. And it's actually a very important step, because otherwise your circle is going to be scuffed. So imagine that you have a bunch of pixels, right? So here is the so the pixels. Let's actually do like a 3x3 row of pixels. I think that's going to be the reasonable thing to do. So, and here is the center of the circle, right? And if you're just taking the center of the circle and try to determine the distance from the center to a pixel, what in reality you're doing, you're determining the distance between that and that, right? If you're just using naively the coordinates of the pixel, right? So, which is not particularly correct. This is not what you really want. this is what you want, right? So what you want to determine the distances between the center of the circle and the centers of the pixels, and that will give you more accurate picture overall. Otherwise, if you're using like this sort of things, right, you're gonna end up with a picture that is sort of shifted to the left and up, right, which makes sense because it's a top left corner of the pixel. So we already do a little bit of a subpixel math in here, but what's interesting is that we're doing that subpixel math in integers, right? Because since we need to determine only the center of the pixel, what we can do, we can just scale the whole resolution up twice, and then basically the pixels become divisible by 2 quite easily in integers, right? So if we're going to do anti-aliasing, so we probably will have to switch back to the floating point math, because I don't know if it's going to be easily representable with integers yet, right? So my brain cannot see that ahead until I actually implement that. So the first thing I want to do, I want to actually rewrite this piece of code back to floating points. Right, and then from the floating points we can see how we can determine what's the percentage of the pixel is occupied by a circle, right? So let's go ahead and do that. So I'm going to just re-implement the entire function. I'm going to call it fill solid AA circle, so it's going to be called anti-alias circle, right? So we're going to accept the array of pixels, right? So this is the canvas into, why is this thing jumping around constantly? Emacs. Are you okay, Emacs? I think Emacs is not particularly okay. Emacs is not okay today. So we're accepting the array of pixels. Also, we're accepting the width and height of the picture, right? We're also accepting the radius of the circle and the foreground and background colors, right? There we go. So this is what we've got. So the next thing we need to do, we need to determine the center of the circle. So the center of the circle is going to be the center of the picture. So we're going to define something like Cx. We're going to take the width, we're going to convert it to floating point, and we're going to divide it by 2 by just multiplying by half. Multiplying by half divided by 2 is the same thing anyway, so who cares? So we're going to do the same with the height. So we determine the center of the circle. And I also want to take the radius and also convert it to floating point, because that will make it a little bit more convenient later. So I basically pre-convert it to floating point. So let's start iterating the rows. All right, so for I in through 0 to height, for x in through 0 to width, here we have the point and x and y. So as I already said, we need to find the distance between the center of the circle and the center of the pixel. X and y is not the center of the pixel. Right, so what we want to do in here, we want to take, you know, some sort of like variable. We're going to take the center of the pixel, and we need to subtract the center of the circle, and we need to subtract the center of the pixel. So here we convert x to float, right, and we add half of the pixel. And that's why that way we compare in center of the circle and center of the pixel. So we do the same for y as well. There we go. And dx is basically the position of the center of the current pixel that we're checking. So the next thing we need to do, we need to check if the square of the x of the center of the pixel plus square of the y of the center of the pixel is less or equal to the square of the radius. And if it is, we will have to set the foreground color, otherwise we'll have to set the background color. And since it's Rust, I can simply take this thing as an expression, because Rust, as far as I know, expression-based language like OCaml, right, or something like that. And I'm gonna assign it to the pixel, right? So it's gonna be pixels y multiplied by the size of the row, which is the width, and plus x. There we go. So I think we successfully re-implemented that entire algorithm, but in floating points. Let's see if it compiles, because as you know, if it compiles, it works. Never gets old, never gets old. Okay, so rust c main.rs, does it compile? Doesn't even compile, so it means it does not work. I forgot equals, of course. Okay, seems good. So now, as far as I can tell, we need to call this function somewhere. So let's call it after we generated the solid rectangle. So let's fill the entire canvas with the green color so we can instantly see all of the mistakes we've made. right? And then I can do fill solid AA circle. I provide all of the necessary parameters. You know, I'm going to actually copy paste this entire thing. It's going to be solid AA circle, right? So something like that. And so we have to provide the pixels. So then we provide the width, then we provide the height, then we provide the radius. So we don't have a constant for the radius, but we usually use third of the width as the radius. So I'm thinking maybe we could actually introduce the constant for the radius. That would be actually kind of nice. So the radius is going to be basically width divided by 3, essentially. Let's find all of the widths divided by 3 and replace them with the radius. Okay, so this is going to be a radius. Here's another radius, there we go. So then we do foreground, and then we do background, and after that, after we generated this entire thing, we want to save it as ppm solid AA ppm, providing the pixels, width, height, and in case it throws an error, we're gonna crash. Okay, so is it gonna compile? Let's see. The winner gets T, that's for sure. So the result is gonna be the same. So these two pictures, solid and solid AA ppm, should be absolutely the same. Let's actually find out if they are. So I think I'm gonna do the following thing. It's gonna be something like solid and a boom. Well, yeah, use the new buffer. So I already actually opened it twice. So here is the first picture, and there is no difference between them, even though like Fair doesn't allow us to sort of like zoom in and not reset the scaling. I wonder if there is a way for like to tell Fair, don't reset the scaling when I switch the picture, but I doubt there is a way to do that. Maybe there is, I don't know. So if I take a look at Fair, I'm gonna quickly take a look at the man. So scaling, so full screen. Zoom only effect. So there is a flag called zoom, right? So zoom images by % when in full screen mode or when window geometry is fixed. When combined with auto zoom, zooming will be limited. So what is the auto zoom? Auto zoom in screen size full. I don't know. We can try, but I feel like it's going to be useless. I already have to provide too many flags to these. Like, you know, there's something wrong with your program if you if you have to alter so many defaults. Excuse me. So I mean, come on. Oh, okay, perfect. Okay, that's actually exactly what I want. All right. So I'm switching between these things, and it's flickering. I wonder if there is a flag to make it stop flickering. Then, like. This is so annoying. Like, why is this program so annoying? Like, why have to alter so many defaults? Why people don't just make a convenient default in the first place so I don't have to change anything? Look at the amount of these flags just to watch things comfortably. Like, come on. Maybe there is a config somewhere. I don't know. I just don't want to change the defaults. Right. Okay, so anyway, so as you can see, it's the same thing, right? So, you know, maybe I can actually sort of like take this entire thing and put it into some sort of like a script, maybe sh, right? So it's going to be in sh, and I'm going to put it like that. And maybe I can just do something like this, right? So I suppose this is all of the arguments that we put into the script, right? So, and then it's going to be plus x, it's going to be feh, and if I do solid ppm, right? So it seems to be working, so I don't have to, like, you know, call this huge command line shit or whatever the fuck it is. So if you want to make a good program, just make convenient defaults. Look at the Blender, for instance. Like, all of the defaults in Blender are absolutely scuffed. And when you have a fresh installation of Blender, like, first hour you spend on just like changing the defaults. It's insane. Just make a reasonable default then. All right. So what do we have in here? Okay, so how can we be determining the like the percentage of the pixel occupied by a circle? Right, so essentially this kind of turns into the problem of figuring out like the area of the square and its like intersecting circle, right? So the area of this intersection, which is kind of too much for, you know, anti-aliasing thingy, because you have to solve this problem basically on each individual pixel, which is kind of like computationally intensive, I think. So I think we're gonna actually cheat a little bit for SenseD. We're gonna simply increase the resolution at which we're basically rendering everything. So essentially for each pixel, we're gonna actually put like some sort of probes at regular intervals. Like for this case, let's actually put 4 of them. We can make it configurable, like depending on the resolution, maybe there will be 9 of them or 16 of them, and so on and so forth. And you have a center of the circle somewhere there, right? And before computing the final color of the pixel, what do? We basically check, is this point, is this probe included in the circle? Then we check, is this point included in the circle? It's actually quite easy. You just basically compute the distance from the center of the circle to that probe, and you do that for all of them, right? So, and then you count how many of them actually in the circle and how many of them are outside of the circle, right? And that way you can know the percentage, right? You can know the percentage of the sort of like roughly with a certain resolution, the percentage of the pixel that is included in the circle. And then you can use that percentage as the alpha channel while you're blending with the background. So that's going to be the idea in here, I think. Yeah, that's going to be the idea. So, but before I go implement this idea, I think I want to make a small break already right away because I forgot to make a cup of tea. I have a cup of water and I thought it's going to be okay, but the more I talk, the more I realizing that I know I cannot survive without my cup of tea. So let's quickly make a... All right, I got my tea, so let's go ahead and implement all of that. So for each individual pixel, so we have 4 probes. But because of the way they're sort of placed, as you can see, right? So they're sort of in the center of the pixel. We're dividing the whole pixel by 3, right? So let's actually have some sort of a parameter, maybe resolution. Let's call it const res, and this one is going to be something like usize. And in our case, 2 means that the resolution is going to be 2 by 2, right? So we're going to divide both width and height by 2. But the actual step in here, right, is basically pixel divided by 3, meaning that so we have something like a step, right, and it's going to be floating point, a res as floating point divided by, it's actually 1 divided by that, plus 1, right? So if we have 2, we have to divide it by 3, and so on and so forth. All right, so after that, we probably need to iterate through each individual probe, right? So because of that, we're going to have it like so. How are we going to call the iterators? So we can call the iterators something like I. So, but maybe we need to indicate whether it's X or Y. So we can have something like AAY, right? So it's going to be in 0 in AA res, and then we're going to have a similar thing for X in here. So we have X and Y. Though since it's a square, it doesn't really matter in which order we're iterating through all of these things. So, yeah. Anyway, so and the actual thing we do in here, we need to compute. So this is the center of the thing, right? So I'm gonna move this entire thing inside, and so now that entire point is essentially X, right? So this is the left top corner of the pixel, and since there's always like a padding between the first probe and the edge, what we have to do right away, we have to add the AA step, right? So we're adding AA step right away to accommodate that padding. After that, we have to add AA X or Y multiplied by this step, right? Multiplied by this step. And so that gives us the coordinate of the probe, right? So maybe we're gonna rename it to PXPY to indicate that it's a probe. Right, so now we can try to calculate the distance between that probe and the center of this circle. So in that case, it's going to be dx, cx minus px, and also dy cy minus py. Right, and if, how to say that, if dx squared plus dy squared is less or equal than the radius, then we need to increment the counter, right? So we're gonna have some sort of a counter in here. AA count is gonna be initially 0, and AA count plus 1. There we go. So this is how many probes lie within the circle. Right. So after that, we need to compute the percentage. And what's going to be the percentage is basically AA count divided by the maximum amount of those things. Well, in our case, it's basically AA resolution multiplied by AA resolution. So AA resolution squared. Right. So if resolution is 2, that means the amount of this prop is going to be 2 multiplied by 2, so there's 4 of them. That's why we divided by that specific thing. But again, so this thing has to be in floating point, otherwise we won't be able to do that, and we're going to have the percentage stored in here. So there we go. And now, right, now we need to assign the pixel by effectively blending two colors together. Right, so yeah, this one is interesting. So the percentage is how far you need to blend into foreground. So let's actually do something like blend pixels. This is a non-existing function yet, so we're about to implement it. And we're blending from background to foreground with this specific percentage. Right, so we'll need a function that accepts two colors and the percentage, and will blend these two colors together. Right, so let's go ahead and implement that thing. So maybe before I go ahead and implement it, I want to check if this entire thing compiles, because I haven't checked that for a while, but we'll see. So this is U32, this is U32, this is U32, and this is the percentage, right? So it has to be F32. And what it returns, it effectively returns the new pixel in here. So let's actually mark it as to do. And let's go, oh my god, Emacs, come on. And let's go ahead and recompile the entire stuff and see if it compiles. It does not even compile because I forgot the semicolon. Oh my god. Forgot the semicolon, another semicolon. Imagine requiring semicolons in 2021. So yeah, this one has to be converted to F32, right? So it's going to be F32, and there we go. Cool. So everything seems to be compiling. So how are we going to be blending these two things together? So the color is 32 bits, but as far as I know, we're just ignoring the alpha. We're simply ignoring the alpha, and the question is, where is the red, where is the green? Okay, so this is the red, this is green, and this is blue. So, and we just ignore the extra byte in there. So one of the things we probably want to do, we want to extract the reds, I suppose. Right, so if we take the background red, so the red is effectively, we shift it down by 2 bytes. So 0 is going to be 1 byte, another one, yeah, so we shift it down by 2 bytes, like so, and then we just take in the mask in here, 0FF. There we go. So that gives us background red, and the same thing has to go to the foreground. So this is the background and foreground red. The final red is going to be basically a lerp between BR and FR. So we'll have to do something like lerp. But before we can do lerp, we'll have to convert it to float, right? So FR as F32, and then we're going to use this thing. Right. Then we're gonna use this thing. You probably can do this kind of stuff in integers, but my brain is actually too mushy right now to come up with the integer solution. So I'm gonna use floats because it's easier for my brain right now. I don't know why my brain doesn't really work well today. It's probably like, it's pretty rainy lately. So yeah, because of that, I'm gonna do everything in floats. Maybe one day I come up with the integer solution. With the integer solution, you probably will just have to scale it up to some sort of degree or something. I suppose. We'll see, we'll see. Do we have a lerp in Rust, by the way? stdlib. Rust stdlib. Do you have lerp? Can you have a lerp in 2021? You don't have a lerp? Really? My god, even C++ has a lerp. Yes, even Z++ has a lerp. Yeah. And Rust doesn't have the lerp. There's also midpoint between two numbers or pointers. Cool. Okay. Anyway, so let's actually implement lerp. So it's gonna be the lerp. You take A, you take B, and you take the P, I suppose. So this entire thing has to return F32. So the way that you implement it, you basically return A plus B minus A multiplied by P. That's it. So that's probably why it is not in the standard library. Like if you need this thing. Yeah, it's kind of interesting. Is it even worth including lerp in standard libraries if you think about it? So if you need lerp, you already know what is lerp, so you can easily implement it yourself. If you don't know what is lerp, like you probably don't even know how to implement it, so you just don't need it. It's kind of a very strange thing to put in the standard library, right? So it's just like never makes sense. If you need it, you know what it is, and you can easily implement it. Like, there you go. Here is lerp. So, I don't know. So lerp, for those who doesn't know, it's a linear interpolation, right? So basic operation of linear interpolation between two values. Yeah, so essentially you take two values and percentage, and it returns you a value between these two values with the certain percentage between them, right? So that's basically what it does. Nothing particularly special. And that's how we blended the colors. And by the way, this is not a correct blending of colors because we're blending the colors linearly. But as far as I know, the colors, the color components in the computers are not stored as a linear values. As far as I know, they're stored as square roots, right? So, and the first thing you have to do before doing linear interpolation between them, you have to square them, returning them back into the linear space. Then you square them linearly. Then you do interpolation on them linearly. And then you square root it back. Right. So maybe because of that, we'll see some sort of like weird artifacts and stuff like that. For more on this information, you can probably watch the Minutes Physics video on this thing. So Minutes Physics color. Right. So I'm gonna put the link. Yeah, computer color is broken. Right. So this is what I'm talking about. So where is my description? So I'm going to put it in here. Every time we're talking about color, I'm redirecting people to this specific video because I think it is a very important video, and it is very important to be aware of this thing. It's okay if you just ignore it, because majority of people ignore it anyway, and for the purpose like of quickly prototyping something, it's probably not important. But I think it is important to be aware of it, right? So it is important to be aware of it. So it's like writing slow software, right? There is nothing wrong with writing slow software if you need to quickly prototype something, but at least be aware of that. At least don't be delusional thinking, oh, it's fast. No, it's not fast. It's like you're doing that intentionally. Anyway, so so here we're doing incorrect thing, and we're doing that intentionally, but maybe at some point we're gonna actually go ahead and fix that. At some point we're gonna go ahead and fix that. I'm thinking, How would you do that in integers? How would you do that in integers? I suppose you would have to first convert this p into percentage, right? And then you'll have to replace multiplication here with the division. So that's probably how you would get rid of the floating point. So maybe I'm going to put a to-do for myself in here at some point if I ever go back to here. So it would be probably better to do the color blending in integers, since we working directly with you know, 32-bit color representation. So sometimes people represent colors in a normalized space by using values from 0 to 1, floating point. In that case, like, it just makes all of the computations easy, and then before outputting that to the screen, they convert to 32-bit color representation. But since we're doing everything in 32-bit color representation, maybe it would make sense to do all of that in integers. So that's basically what I'm saying in here, without like conversion and stuff like that, because you have to constantly convert between integers and floats and so on and so forth. But we're not here for the speed anyway. Okay, so this is only one component, and you want to sort of save that component like back. But before we can do that, I think we need to do that for all of the components. So this is going to be green, and the green is located at the first byte, right? So this is the first byte, and then we're going to do that for the blue as well, right? So this is going to be blue, blue, and this one is located at zeros component. There we go. So now what we need to do, we need to assemble back the color, right? So we need to assemble the colors back. How are we going to be assembling them back? We're going to take the red color, we're going to shift all of that back to here, then OR, and we're going to take G1 or B0. There we go. So we extracted all of the components, we blended them with linear interpolation, and then we assembled them back. And we'll kind of have to do that on each individual pixel, which is probably expensive, but again, we're not doing super like high performant computations, so maybe it doesn't really matter. Okay, so let's see if this entire thing compiles. It does not compile. I wonder why. So, oh yeah, this one is float. So before I can continue, I probably need to truncate it down to U32. And I'm thinking maybe I could actually, nah, it's fine. All right, so yeah, so we caught a bug. I'm not using these things at all. Yeah, this is that, and this is blue. Right, there we go. Okay, it compiles. And as you know, if it compiles, it works. Okay, so let's see if it's gonna even, you know, produce interesting results. It was actually relatively fast because the resolution we're generating is 256 by 256. It's actually kind of small. We can crank it up a little bit higher and see what's going to happen. Right, so this is going to be something like that. So first, let's recompile to separate the time between compilation and actual generation. And there we go. Okay, let's take a look at if that thing generated anything significant. Okay, so this is... okay, I think it works. Okay, so here is the original thing. And here is anti-aliased one. Okay, so it actually works. Yeah, so we have anti-aliasing in here, but it's kind of strange, I think. So the jump, there is huge jump between the alphas of the values. Right, I think it's too huge. I think it should be a little bit more subtle. And the reason why it is so huge is because, again, I think we're blending the colors incorrectly. Yeah, I think that's precisely the reason we're blending colors incorrectly. And to blend them correctly, we need to try to first square them before blending, right? And then square rooting them back. I think that's how we do that. I hope it's not the other way around. Yeah. Okay, so let's actually go ahead and do that. So in here, I'm gonna just go ahead and square them all. Gotta square them. I'm sorry. So it's gonna be BG. BG, and FG. So this is gonna be BB, FB. But then I need to take a square root of this entire thing. I wonder if we have a square root in the standard library in here. So we do have a square root. You look at that, and it's a method, which makes it rather convenient because now I can just do square root like this. Right, so I do lerp and then I do square root. Yep, and then I'm truncating it to U32. Okay, let's take a look, and maybe that will generate something more linear. Yeah, probably. It would be interesting to compare those things, right? So different ways of interpolating and shit. Yeah, that would be definitely interesting. Also, if I reduce the entire resolution and make it very, very small, since we have this flag -z, I think Fach is gonna stretch it up and show like more interesting stuff for us. So let's actually go ahead and do that. I'm gonna recompile the entire thing. I'm gonna rerun, and it's pretty much instant. Yeah, now we can see shit. Oh, that's cool. You can, yeah, you can now see the differences. Yeah, that's actually very cool. I really like that. Look at that. Yeah, you can clearly see. You can clearly see the differences between aliased and anti-aliased. That's so cool. And the cool part is that it's actually really easy to fucking implement, right? You just count those things and shit. I want to compare it with incorrect blending of the colors, right? So if we're not doing this gamma correction thingy with square roots and whatnot, how is it going to work? So this is blend pixels, let's call it gamma corrected, right? So this is one thing. So blend pixels, gamma corrected. And I want to create something like blend pixels naively, and I suppose I can just go ahead and just grab the entire thing in here, like so. And this entire thing should probably return the U32. So, and in this particular case, we're going to just copy paste the entire thing and revert it back, right? We're going to revert it back. We're going to get rid of these squares. I wonder if I can easily do that, like so, right? So it's going to be like this, a boom. And something like this. Emacs magic, everyone, by the way. Can your Vim do that? I don't think so. So you can blend pixels gamma corrected, or you can blend pixels naively. So now I want to have some sort of a parameter in the fill solid AA circle that lets us choose between gamma corrected blending and not gamma corrected blending. So I'm thinking how we can do that. Maybe we can pass blend pixels as a pointer to a function, right? So I don't remember how we do that. So do you do that as a fn? In Rust there's a lot of things like a fn mute, a fn once, and so on and so forth. So you have a fn once, call operator takes by value receiver, can be called but not be callable, mute multiple, cannot be callable multiple times. So I think we need a fan because I think it should be callable multiple times, right? So the call operator detects an immutable receiver and still can be called repeatedly without mutating the state, because it doesn't really mutate any state, right? So that's precisely what we want in here. So we want a function that accepts, right? what does it accept? U32, U32, and F32. So let's call it maybe like blender. Can I just say it's a blender? Yeah, and that means it's a generic, right? So we have a blender, and then we can say where blender is is a fan that accepts F32, U32, U32, F32, and then returns U32. Right, and then I can say blend pixels, right? And when I call this function, I'll have to provide the specific blender, right? I'll have to provide the specific blender. Okay, let's actually try to compile the entire thing and see if it's gonna work. If it's gonna work now, yo, blend pixels gamma corrected, right? So, and it seems to be working. Yeah, so now it complains that we don't even use naively. All right, so what we're gonna have in here. So we're going to do the following. I have a fly in here. The following thing in here. So this one is going to be gamma corrected. So this is a gamma corrected thing. And we're also going to have. Why do I have a fly in here? I need to kill this fly at some point, but not on the video because that's animal abuse. So okay, naively. Naively. All right. So as you can see, I'm using the same function, but I'm just parameterizing it with the blend pixels function, right? So and hopefully that will produce something more reasonable. And let's try to render everything and let's take a look at that stuff. Okay. So gamma corrected naively. Okay, that's very interesting. This is the naive approach, and this is gamma corrected. So you can clearly see the difference. You can clearly see the difference. Right. So, and that's not anti-aliased at all. Huh. That's very interesting. So naive approach looks a little bit smaller, right? So you see, here's the naive one, here's the gamma corrected. Naive one, gamma corrected. Naive one, gamma corrected. And here is the gamma corrected anti-aliased and not aliased. So the gamma corrected one is closer to the solid not aliased one. So it's just like a little bit closer, right? And more explanation on how that works and what's going on in there is in the minus physics video. So I really recommend to watch this one. So okay, apparently it was important. The final result actually makes more sense now. It in fact makes more sense. That's pretty cool. We can try to crank up the resolution, right? So where is the resolution? I mean, resolution of the anti-aliasing, right? So right now we're using like the resolution 2. We can put 3 in here, right? Maybe we can actually make it parameterizable as well. So this function starts to get a lot of parameters. Right, because you need to parameterize like the pixels and the size of the canvas, the radius of the thing you're drawing, the foreground, background colors, and the pixel blender, and so on and so forth. So, and we'll have to add now a resolution. So it keeps growing, it keeps growing. All right, so it's gonna be Rust C main.rs, and let's see what's gonna happen. Okay. So I increased the AA resolution, right? And is it gonna make too much difference? I wonder. It's hard to tell if it makes too much difference. So I suppose, I guess it's gonna be just more smooth, but it's hard to tell how smooth it is going to be, right? Kind of hard to tell. Anyway, that's pretty much it, what I wanted to do for today, right? I just wanted to explore this very naive, simple anti-aliasing approach, and it works fine, I suppose. And it seems to be, I think it would work for any kind of shape, right? So essentially, it's basically increasing the resolutions of the computations, right? And then using that higher resolution to produce the blending between the colors, background and foreground. So that's essentially what this simple anti-aliasing approach comes down to. So yeah, that's how we do that. That was actually pretty cool. I really like that. Anyway, so did I put this thing in the description? Let me see if I did. Okay, so I'm gonna put it here. Simple, simplest approach to anti-aliasing, right? So you will be able to find this link in the description, right? The source code is going to be available also in the description. So, and I guess I gotta go. Thanks everyone for watching. Love you all. Mwah.